So as I said, let's see, last time, I'm an experimentalist, if you weren't here yesterday, and we do a variety of experiments that don't fall in the category of making a quantum computer, but sort of fall in the quantum information sphere. So in our experiments, we control the motion of nanomechanical elements. That's sort of what I was talking about yesterday, and also the motion of neutral atoms, and these both lead to some perspectives on what we can do quantum-wise in these systems. So we had this theme in day 1 and day 2, where we were basically talking about this optomechanical system, where last time we went through and said, well, okay, here's the Hamiltonian for this optomechanical system, but we're in a regime where a single photon doesn't really have a very large effect on the motion of this mechanical object. And so we linearized the system, got rid of what many of you might think of as the interesting coupling, went to this linearized regime where we could have beam splitters, photon-phonon exchange, squeezing, look at an interferometer, and then yesterday we looked at sort of these quantum limits to interferometry. And the same formalism will apply to this idea of quantum transduction. Here we also have just this basic linearized system where we have this weak nonlinearity, but that's sufficient if what we're going to say is, well, we have some interesting state that we're going to get from a superconducting qubit where there is a strong nonlinearity, and then we'll send it through our mechanical element and get something out the other side. So we went through this machinery of the weak nonlinearity yesterday, and we talked about quantum metrology, and today we'll talk more about transducers. And then tomorrow, and maybe I'll start this a little bit today, we'll talk about ultracold atoms sort of from a qubit perspective. Okay, so I'm not saying a neutral atom quantum computer, because that doesn't exist or is quite improbable at this point, but sort of from a qubit perspective, how do we think about things we can do with neutral atoms at this point? Alrighty. So maybe just a little bit of a review from last time. These references were scattered about the talk yesterday, and they should be online at some point. But just as a few things that were relevant, there's sort of optomechanics reviews that talk about this general coupling, but hopefully the goal was to talk about a little bit more general themes of quantum metrology. So there's a variety of interesting articles. This review of modern physics by Ash Clark is nice. We talked about the Caves House theorem and did our really simple derivation of that, and that's the reference for that guy. The experimental data that we talked about that was specific to this question of how do you set your detector up correctly, that can be found in this paper here, where we're trying to think about broadband displacement detection and quantum limits on that. Any sort of lingering questions from yesterday? Yeah.
So you commented on how current experiments are still pretty far from single photon strong coupling mechanics. Could you comment on whether there are any prospects to reach that in any of these different physical systems?
Yeah, so I would say it could get there. And so I would say for a really solid state floppy thing, experiments are about a factor of 10 away. So you can decide for yourself whether that factor of 10 is a problem or not. In our experiments, we're factors of thousands away, right? So there are experiments that are much closer. And in general, there's a continuum of, basically it's sort of about the mass scale, right? And the limit of, you can sort of think of an ion as an optomechanical system too, and that's a very small mass limit. And people are also using sort of beads of particles that have a much smaller mass as well. Yeah. Okay? All right. So yeah, with that in mind, I think a lot of the questions at the beginning of the last lecture were sort of about the parameter space that was relevant as we were thinking about this basic interaction. So maybe I'll just review some of the basic interaction and talk about a little bit of the different scales of the different sort of frequencies that are involved. So remember, we have this oscillator here that we're just writing as a mass on a spring. It has some spring constant. People were telling me that symbols were showing up strangely last time. Seems like they're there. Okay. And so we have some spring. It has a resonant frequency omega m, and there's a mass of this object that's associated with it. And we thought about, all right, all that's going on here is we have a force, and we have some coupling factor g that's related to how much will the cavity frequency shift if we put a certain amount of displacement change to the mechanical element. So the shorter the cavity, the larger that g factor will be. And then we have the photon number in the cavity, and I'm always using A to refer to the annihilation operator for the cavity mode. Although I will start swapping up these different letters when we start talking about microwave cavities as well when we talk about transducers. Okay, and then we define this G that had the 0-point motion sort of baked into the expression so that we can get a sense of scale of these systems. Okay, so that's our 0-point fluctuations, and then we wrote down the interaction as a coupling between the photon number and the mechanical position. So B here is always for the mechanics, and I'll try to keep that consistent throughout. So last time we talked about how to sort of quickly think about linearizing this and getting a beam splitter interaction, two-mode squeezing, or think about it as an interferometer. And sort of the scale of the problem here in terms of the different parameters involved, that's supposed to be a Lorentzian, though it looks like a toppled over hat. So there's this cavity response that is defined by some kappa. So that's our frequency scale for the cavity. So if I were to write a cavity susceptibility, we would have kappa over 2 minus I, delta referring to the frequency shift with respect to the center of the cavity resonance. And that factor of 2 is always there because we choose kappa to mean a certain thing, in this case the full width of this object. Okay, and so in terms of other scales that are involved, if I think about the drive, so I sort of have here the frequency of the laser that might be detuned from, say, the resonant frequency of the cavity that's at the center of this response here. Okay, and so we define this delta here to be that laser frequency minus the cavity frequency. And I guess I should call that a capital L. All right, and we talked about this resolved sideband limit where we thought about, can we get the mechanical frequency greater than this kappa? Okay, so that would allow us to, let's say that we're driving over here. Okay, this is our laser drive position. Then we can think about sidebands on this laser drive that would be at the mechanical frequency. And so those sidebands would show up over here and over here. And we talked about the difference in the force fluctuations at this position and this position, and talked about how that led to cooling. Okay. And there's various factors of 2 in here, but this resolved sideband limit was, for example, how well we were able to cool in the end when we were talking about the cooling. And so these same sort of parameters will come in today. So maybe just a little bit more about numbers here. So these are maybe just some numbers for our particular optomechanical systems, and we showed that plot last time where we had nano and macro and medium scale mechanical systems, and I'll just write for our devices what numbers turn out to be. And these will be relevant as we go forward and talk about transducers and also microwave couplings. So the scale of this kappa number is, I always have the 2 pi in there, is about 1 megahertz, and that corresponds to sort of a millimeter scale cavity with a finesse around 10,000. So finesse for an optical cavity is how many times the photon bounces back and forth between between the mirrors. And to get that, we actually use really high-quality mirrors that scatter about a part per million of the light. And if you drive out to East Boulder, you'll find a bunch of companies that do a really good job at making coatings that only scatter a part per million of the light. Okay, the mechanical frequency. We talked about these mechanical elements that we use that are these high-stress objects. They're also on the scale of a megahertz, a little bit larger. We calculated the 0-point motion for these objects, and it's on order of a femtometer, so 10 to the minus 15 meters. For a sense of scale, if I compare that to a trapped ion, the 0-point motion is sort of tens of nanometers. The sort of absolute scale of the cavity frequency shift is about 20 megahertz per nanometer for our particular experiments. And when we put that into units that are this G that we put in the other expression, that corresponds to about 10 hertz. And the fact that this 10 hertz is pretty small compared to, say, kappa or sort of other scales, then that's basically a statement that our coupling is pretty weak. But if we take this sort of optomechanical, you can call it a photon-phonon exchange rate or a cooling rate that we wrote down as 4 times the photon number in the cavity, g squared over kappa. That value, depending upon how much light you put in the cavity, can be up to sort of 10 kilohertz scale. Also with the mechanical element, we want to think about what the mechanical decay rate is. And remember, we talked about these mechanical things are very high Q. So that gives us sort of a 1 hertz scale or even 0.1 hertz scale for the mechanical damping. And so that's actually much slower than, for example, the cavity decay. All right. So that's a scale for the optomechanical system. And then we talked a bit about these mechanical elements that we use. They're the silicon nitride drums. I put a new picture up here to show you the scale of it. You can sort of hold it in your hand and you can see the light reflecting off of it, and you can see this thin film that we're using. But it's very, very thin. So as we talked about last time, it's sort of 0.5 millimeter on a side and about 50 nanometers thick. So we talked about how these objects can have very high quality factor, and then also about this idea of thermal noise. How do we make sure that this thing that we're holding has a continuum of mechanical modes, and how do we understand all of the mechanical modes that are there, and why is it that we can actually measure only one of them and control one of them and not have all the other ones get in the way? And we talked about band gap engineering, phononic band gap engineering, in order to sort of push away the modes that we don't want to be there. But then also the spectrum of the really low mass modes of the system are really these particular drum modes of the silicon nitride membrane. And so if I think about this object, it's actually dominated by a scale which is the stress of the thin film that we're using, which is a gigapascal sort of scale. And the density of the silicon nitride is 2.7 grams per cubic centimeter. And if I write down what are the frequencies, resonant frequencies of the modes of this object, well, it's this drum, and so I have a fundamental mode where the whole thing would go up and down. And then I've been talking about this particular mechanical mode because it turns out to be often a high Q mode, and also for the transducer stuff that we'll do, it turns out to be handy to have multiple antinodes. But if I were to write out an expression for the frequencies of this object, it's like a 2D string where the mass density comes in, the length of a side, and this stress of the mechanical material. And so what's really useful about these objects is the resonant frequency when they're really stressed is megahertz scale. But if you were to relieve that stress and it would act more like a bridge, this mechanical frequency would be about a kilohertz. So there's a very big sort of increase in the oscillator energy that you get when you stress this mechanical element. And I think about that as sort of useful for these quantum type experiments because I'm sort of increasing the oscillator scale compared to the thermal scale while keeping the dissipation about the same. For force sensing, that doesn't end up being useful unless you care about the absolute frequency at which you operate. But in general, as an experimentalist, I've sort of sworn to never do an experiment that I don't need to do that has a frequency less than a megahertz. It's always useful to work at higher frequencies. You aren't worried about seismic noise or these sorts of things. So this tension allows us basically to increase the mechanical frequency and keep the dissipation constant, the dissipation defined by this gamma m. Now it's not exactly constant, it's sort of approximately constant. The sort of bending distribution of this object changes as you change the stress of the film.
This m and n goes from 0 to...
Yeah, so the fundamental mode is 1, 1, yeah.
1, 1.
Yeah, so we're using a different convention here than optical modes. And so I would call this guy here the 2, 2. We started doing this at some point and never stopped. Okay. All right. So that brings us a bit to the next topic, which is this idea of the quantum transduction. So I'm going to talk about this story very much in this picture of thinking about mechanical elements that can couple the electrical and the optical domain. But it's a much more general problem. But as we went through all the machinery to understand optomechanics yesterday, then we'll go ahead and do that. So I'll talk about why I would want a quantum transducer and where that idea is coming from. I'll talk about the experimental system that we're working on. And this is very much in collaboration with Konrad Lehnert's group that is also at JILA, and he does microwave superconducting circuits. I'll talk about the experimental hardware, the cryogenic optical system, and then basically the middle of the talk will be about an idea aptly called sort of input-output theory in the context of understanding a quantum network, basically. And this will be sort of machinery that we need to think about things. And the middle of the talk will seem a lot like electrical engineering. Okay, how do I understand scattering parameters? And but this is really sort of the stage these experiments are at, and really what the formalism you need in order to understand sort of how quantum enabled is your particular system. So right now we're not transducing any quantum states. I'm not going to talk about interesting non-classical states going in, but I'm going to tell you sort of how close we are to a domain where we can take an electrical superconducting circuit signal, hopefully ultimately like a single photon, and transduce it to the optical domain. Then I'll talk about experimental measures of efficiency and added noise. And then I'll talk at the end about sort of the most recent things that we've been doing, which is another way to remove noise through measurement and feed forward. We've been talking to Graham and Liang about these ideas as well. Okay, so the basic idea of these experiments that we're thinking about are, well, if we have the microwave domain where you're going to hear a whole series of lectures, or you already have, about superconducting qubits, how great they are. They operate at the bottom of a dilution refrigerator. And so they obviously require ultra-low temperatures given the frequency scale of the object. And if we could take the states that are made in the superconducting qubit domain and transmit them to the optical domain, maybe that's useful for quantum communication type things. 5 years ago I might have said it's also useful because in the optical domain maybe you have better memories. I'm not sure that's really true anymore, but certainly there's some beauty to taking the quantum state to a domain where at our room temperature environment it's not subject to the noise. Okay, or the noise isn't very large. Okay, so we sort of think about this from a couple of perspectives. One, this point that I just mentioned of, well, if I take my light out of the dilution refrigerator, then I could maybe use it as part of some quantum network where those pink boxes are maybe some nodes of that. We've also been trying to understand more recently in terms of different architectures. This is I don't know, some picture we dug up from somewhere that's showing, well, maybe even in the sort of microwave domain, even if you're cold, it might be useful to have optical interconnects. Maybe with the long wavelength scales of microwaves, crosstalk could be important ultimately as something that you care about. And so maybe we even want to think about this as a technology that would even stay at the bottom of a dilution refrigerator and could be helpful. That's all questionable, but the idea is to try to bring this technology to some possibility. All right, so I'm talking about this in the context of a optomechanical system because what we're proposing to do is actually take a signal from the microwave domain, convert it to the optical domain, actually through a mechanical intermediary, using the couplings that I've been talking about. All right, so let's say we imagine that we have a mechanical element. So I'll sort of try to sketch some mechanical thing. Let's say oscillating with this mode that has these two antinodes. And let's say that we couple one part of the mechanical motion to an optical cavity, so exactly the same coupling that we were talking about yesterday. That we found that we could measure that mechanical motion very well. We could cool it. We could squeeze light based upon that. We could efficiently get information out. And so if I try to draw an optical cavity, that would look like this, I guess. Okay, so we have an optical cavity and we have our mechanical motion inside of that. And this is grossly over-exaggerated, why I gave you those numbers earlier. The mechanical motion is femtometer scale if we're at the 0-point fluctuations, and there's obviously some standing wave within the cavity that has some larger periodicity. All right, so what we can imagine doing, though, is we could also take one side of this mechanical element here, and we could put some metal on it, and we could make that part of a capacitor plate. So if we imagine that we then have a microwave system that is an LC circuit defined by a capacitance between those two green things and an inductance where I have a really horrible inductor there. That's defined by some lumped element thing that's going to exist on some circuit board. Okay, so we have an L, and we have a C, and we have a resonant frequency of that LC, obviously 1 over squared LC, and that resonant frequency for the electrical system can be modulated by that capacitance. And if we think about a port for our electrical system, we can inductively couple to that LC. And it turns out that this interaction here is exactly the same formally as the interaction that we talked about yesterday, the optomechanical interaction. And you can imagine that there are some wildly differing parameters that you might get out of this system if you sort of think about the scale of a microwave wavelength, and then you think about the scale of this mechanical motion. If you thought about sort of a bulk 3D cavity, you would imagine that this mechanical motion would have very little effect on that microwave cavity. But actually what we do is use a lumped element circuit, and you can end up with really strangely similar parameters to our optomechanical system in terms of the effective kappa. Yeah. Yeah, so the electrical circuit it's connected to a transmission line that's over here, and it's inductively coupled through those two inductors. Yeah, so the top part, that's just floating, and you can if you sort of bend that image, you can think of it as two capacitors in series. So it's a tricky way of allowing us to just have that top part not electrically connected. Okay, and then, oh yeah, here, let me draw our optical port as well. So if we think about this as what we refer to as a one-sided optical cavity, so in principle both of those mirrors could transmit light, but ideally we would want just the mirror on the bottom to transmit information out, and then we would connect that over here to sort of our optical transmission. So if we want this to operate in a domain where we could really think about it as a quantum transducer, we would think of the requirements as being sort of threefold. You would want this to be a bidirectional process, right? You want it to be capable of doing things that are unitary. And you want it to be efficient. And that's certainly something that takes quite a bit of work to make these very efficient. And efficient would mean photon number preserving. And then we also want low added noise. And you could imagine this mechanical element that I just drew there. It's at megahertz frequencies. And so even in a dilution refrigerator, in principle, you would think that is thermally occupied. And so that's a good way that you could add noise to this transduction process. But it turns out exactly this optomechanical coupling and the difference of the rates that we've been talking about should allow transduction through the mechanical element at rates that are relevant. We can talk a little bit more about those parameters. So sort of these are the three things that we want. And I'll talk about, a lot of the talk will be about how we measure how efficient this system is and how it compares to sort of other systems. So this general idea of having a system where ultimately what we're going to do is we're going to put some microwave signal in. It's going to end up as a sideband and an optical signal. And if I have a lithium niobate modulator, if you're an experimentalist, you probably have one of these on your optical table if you use optics. And this does basically exactly the same thing as what I was talking about in the previous slide, except for if I were to calculate the photon number efficiency or find out what it is for a typical object like this, even the most optimized objects that there are, it's sort of like 10 to the minus 3 or something for your typical modulator. But people are certainly working hard to try to improve this and achieve higher efficiencies. One thing that I think is useful about the micromechanical motion is, remember yesterday we talked about how our optomechanical system can create this ponderomotive squeezing. In that way, you can sort of, you can think of the optomechanical system as effective nonlinear medium, where you get to define the sort of parameters of that nonlinear medium by engineering the geometry. And so I sort of think of the reason to use micromechanical motion is we're able to engineer these systems. And there's a certain amount of flexibility in materials and geometry that may help us, may hurt us. We'll have to see. Okay. And so this is just a sampling of other things that people are trying to use to basically make an electro-optic device that would be compatible with superconducting circuits and the transduction of quantum information. So there's sort of attempts to make lithium niobate type systems that are bulk into an efficient modulator. There's work at Yale on sort of other nonlinear media, aluminum nitride, piezoelectric couplings can also be relevant to this problem. So the coupling that I'll talk about is very relevant to the framework that we've developed and what we're doing, but there's a lot of other things that people are working on to try to solve this problem. Okay. All right, so in our systems, what we end up doing in order to do these experiments is we want to operate in a dilution refrigerator. That's where, say, the superconducting qubits would operate and send their signal down some transmission line to a converter. And that converter will also operate at cold temperatures. The microwave occupation will be small, and also the mechanical thermal bath will be low temperature as well. So this is the dilution refrigerator that we work with, and there's a little copper box on the cold part there. And there's a cavity and some other optics and microwave things that exist inside of that copper box. And in this particular system, we have a way to take optical light, manipulate it around on an optical table in sort of how you usually would, and then we put it directly into the dilution refrigerator through a window. And so, the modern way of doing optics is to use optical fiber, right, to guide the mode. For a variety of reasons. It turns out experimentally there are some nice reasons to like to use free space. For the particular cavities that we use, these, yeah, question.
It's like two parts. What happens if you don't cool it down to cryogenic temperatures? And also, what if instead of wanting to use this as some kind of transducer, I simply wanted to use like the cold optical environment to cool some ambient microwave environment?
Mm-hmm.
Is that possible without just sticking it in the dilution refrigerator?
Yeah, okay. So maybe the second part first, from sort of a fundamental perspective. I think what you've hit on is indeed true. I can think of the optical bath as sort of a effectively colder bath than the microwave one. And indeed, there might be very interesting things you could do there. Whether I can practically operate this not at cryogenic temperatures. So what we use for all this electromechanical coupling is actually superconducting thin films, and those need to superconduct in order to operate. And I could make bulk microwave cavities, but then I worry about what the coupling actually is and how big it is. So practically these things only work cold, though we've operated them at 4 Kelvin with an niobium thin film. Yeah. Or is that what you're asking? Okay. Yeah, so the thin film that we're using is niobium, and I'll sort of show some pictures that show that thin film later. And recently we've actually been doing work with niobium tinitride as well in order to deal with some noise problems that we've been seeing, and that also has even higher TC. And that TC can be important when, so the biggest question in all of this is, for any device that you might want to try to do this with, you're going to be putting a lot of optical photons in, depending on how large your coupling is to the mechanical system in this case. You have to put a lot of optical photons in. Those optical photons will scatter at some small level, but any optical photons hitting the superconductor can be a problem. And the higher TC that thin film, probably the better that is. Yeah.
So I was curious about a couple of things. One is I was hoping you could elaborate on why you want to go free space, because it seems like if you were to make this into a practical device, you would want fiber-based couplings just because they're more straightforward. But then also I was wondering about sort of the size scale of the transducer relative, and all of the sort of associated component parts relative to sort of the size scale of these superconductor qubits. Is this something that you could feasibly fit into, John Martinez's machine or something?
Mm-hmm. Yeah, so a couple of answers. So on the optical side, yes, any commercial sort of set of systems is ultimately going to want to use telecom wavelengths and optical fiber. For our purposes, we use 1064 nanometers because that's where we get really low noise lasers. And then also, I don't know, my motto is free space is a good thing in quantum optics because nothing happens there, right? And so I think that the fiber, there can be weird scattering processes that sometimes occur, and they're also using 2 polarization modes can actually be sort of annoying fiber as well. So that's why sometimes I like free space, but indeed if someday this worked and you were to commercialize it, then you better use a fiber. Okay. And you also don't have to put actuators at the bottom of the dilution refrigerator. That's another practical element. We can just use the mirrors that are over there and then steer into the optical cavity. Okay, so the second question, this is what the box looks like that holds the whole transducer. And it's not totally different in scale than these 3D, 3D cavities made of aluminum that hold the transmon qubits. Whether that's a good idea in the end to have many of those, I don't know, but that's the scale of what we need right now. Okay. And yeah, a lot of it is about the microwave coupling defines the sort of scale of the box. Okay, so the base temperature of the system that we use is 40 millikelvin, and you can imagine that you stick light down the system, and then it hits this mechanical element, and if that were to absorb a lot, and the thermal conductivity of the film were to be small, which it does get smaller as you go to colder and colder temperatures, then you can imagine you just heat up your mechanical element. But we actually see empirically the Brownian motion is thermalized to the dilution refrigerator temperature down to about 100 millikelvin. So it seems to work well in that way. Okay. So a little bit about the mechanical motion when we do this thing where we couple both to the optical system and to the electrical system. So what we do is we put some niobium thin film in a portion of the mechanical element. We put some on top of the silicon nitride membrane, and then we have an optical spot that probes another part. And this is a numerical calculation of what the mechanical mode looks like when we put some massive niobium film in part of it. But it basically is fine, and the stress stays just fine on the silicon nitride. So this is a picture of one of the actual chips that we make that has a niobium thin film. It's a funny shape in this particular picture. And then it has the silicon nitride membrane, and then it's all connected to a silicon substrate. And so when we do the experiments, we put the optical spot so it hits somewhere over here. So the light is in the Fabry-Perot cavity interacting with the membrane over there, and then the niobium thin film is over there. And then what we actually do at the moment, and this is a little bit kludgy, but we take that chip that has a mechanical element on it, and then we plop it down on top of another chip that has an inductor loop and the other capacitor pads. And we make the space between those capacitor pads on order of a few hundred nanometers. So this is what it looks like when we put the two things on top of each other, and we put this sort of smaller chip on top of the top chip, and we try to get this separation what we need it to be. So that's what our electromechanical device looks like. And then we couple microwave signals into that electromechanical device, actually via a loop coupler there. And then we put our optical cavity mirrors around this mechanical device. And the way that we do this is we use mirrors that we sort of epoxy into a large-scale structure. And those mirrors are, like I was saying, you can see, that's a little bit of a funny image, but this is sort of the front face of one of the mirrors. And that's a super polished surface that has sort of a part per million scattering, and has about a length of 1 millimeter. And then the light bounces back and forth in there about 10,000 times. And then we put the membrane within there. So you can think of this hole inside of the cavity as sort of our optical port, and then the microwave port of the device is one of these cables. And we actually have 2 ports of the optical device that we use for various calibrations, so we can look through the other mirror as well, though information is key here. We want to get all the information out, so we would like the one of the optical ports dominating. Okay, so let's just review briefly the coupling that we were talking about last time in the context of driving with a large red detuned tone. And then we'll get into, okay, I want to understand this whole system, and I want to understand the coupling of all the different elements to the bath, this cold bath that's defined by the dilution refrigerator. And I want to understand really something that we didn't talk about in a sort of quantitative fashion last time, which is how do I get from the fact that I have a propagating field coming down a transmission line, and it hits the port of a cavity, and what happens, and sort of what's the formalism in which I deal with that. So this electromechanical system, I guess this is the first time I've talked about it sort of separately. It also has a coupling that turns out to be about 10 megahertz per nanometer for, say, one of our typical devices. And so that is on order of what we get in the optical device, and so we have an interesting parallelism. And here, let's see, I think I'm going to start using A for the microwave mode, because ultimately the microwave mode is sort of the one that we'll be starting with. B will stay the mechanics, and then I think I'll use C for the optical eventually. So we have an electromechanical coupling that includes the translating between that big G and the little g with the 0-point motion. We have this amplitude alpha that we talked about last time. And then we have sort of a beam splitter interaction between the mechanical and optical modes. And then we have a completely parallel thing within the optical domain. And we are going to now start subscripting all of our kappas with either O or E to refer to an electrical or optical part. Okay, so we have a G optical, and then we'll describe the amplitude of this drive for the optical domain with a chi. All right, and so then we have this coupling on the optomechanical side. And then when we put this together, now we're going to have sort of three coupled oscillators. We talked last time about basically 2 coupled oscillators. So now let me tell you a little bit about sort of the structure that we use when we think about what I think of as the equations of motion for these coupled oscillators, and then also the fact that we're going to send some field in that's propagating down either a transmission line or in free space, and then it's going to hit the cavity, and then how do we think about the different couplings that are involved. So let's say we have, oops, all right, some input field A in and output A out for this transmission line here, and then that dot represents port, and then that's ultimately coupled to our system, but also in that system there's internal degrees of freedom that we also have to keep in mind. And in the context of our optical system, we could think of our port as one of the cavity mirrors, and we can define, let's say, C in and C out to help us understand that coupling. And ultimately what we're going to be interested in is what we refer to as scattering parameters that tell us the ratio of these ANs to AOuts, or say the ratio of C out to AN. Might be what I care about for the transducer. So we'll talk about here this input-output relations. So let's first describe the equation that I would use that relates the output field to, say, the field inside of the cavity, this A. And I would have both of these time dependent here. And so this is sort of my input-output relation that ultimately comes from calculating that things have to be unitary ultimately. Okay, so I write this kappa external here. So this is sort of microwave engineering language for how I think about coupling to my transmission line versus coupling to those internal degrees of freedom. So I've talked about so far only sort of a total kappa that describes the line width of, say, the optical cavity. And that has 2 components. That has this kappa external and a kappa internal here. Right, but if I'm talking about the coupling of those particular A in and A out that are going down the transmission line, then I only have the kappa external part that's doing that coupling. Okay, but I also have a coupling via this kappa internal. In terms of units, it's useful to keep in mind. So this A dagger A, right? That is the number of photons that are in the cavity. But if I want to think about these propagating modes, then this actually, for this input field, this will have units of number per second. Okay, and if you look at that equation, then it makes more sense that I've thrown in something unitful there, and those A's actually don't have the same units. All right, so if we go back to our basic coupling from before, we can sort of briefly discuss how we think about getting equations of motion that take into account the coupling out from the cavity, right? Either to these internal degrees of freedom or externally to the transmission line. And I'll just sort of sketch some of the components of how we do this. And if you really want to solve all these equations, they end up being linear, and you can just plug them into MATLAB. But it's a lot of symbols and matrices to do that. So let's just write down the basic coupling here. Okay, and so our equation of motion will just be this guy here. I'm dropping the hats for now. So the time variation of A will go as that commutator. In order to get out an equation from this, we have to calculate the commutator of A dagger A with A, we get minus A, and so our equation here would be just some equation of motion coupling the B and the A. And we can do an equivalent thing for our mechanical degree of freedom, and we would get this guy here. Now, these equations here, they don't yet incorporate any coupling to my external ports, right? And what I can do, though, is I'm just going to write down here something called the Heisenberg-Langevin equations, which you can basically note as, okay, it's clear what I did there, right? I just did the usual equation of motion, and now I'm going to add some terms that ultimately come from dealing properly with the coupling to these external things. And so the equations will look like this. I have kappa coupling there, or a kappa term there. Same term as above. And then kappa external for AN, where AN is that propagating field along the transmission line that we ultimately care about, that we put in. And I'm just going to use AO to refer to sort of the internal mode that might be relevant. And then I can have an equivalent equation for mechanical mode. Remember, the mechanical damping, I would refer to that as big gamma M. And then we also have a coupling to the environment for the mechanics through this term here. So these equations here, we can linearize them sort of as the same idea that we talked about yesterday, where we have a strong classical tone and then some fluctuation on that, and then we end up getting rid of this term here, and then it turns out that the equations are easy to solve, and then we go back and we use this expression here to get A out, and then we can say compare A out to AN or any of these other parameters. Okay, so that's the typical formalism. And so that's only in the context of two of these oscillators, the mechanical and say the microwave. But if I were to draw sort of all of the different oscillators involved in this problem, I might consider sort of this three blob picture where we have electrical, mechanical, optical, and we would have some what's referred to them as A, B, and C, because I always want to refer to the mechanical as B, and I've switched talking about the electrical as A, and then we'll call the optical C. And so we want to consider that we have some AN as a function of time, though in general we end up often solving these equations and caring about them in the frequency domain, so those also can be a function of omega. And then we have Cn and C out. And then we think about, we also have, let's draw a big, this is our environment. All right, so that's the environment. And all of these different modes are coupled to that environment, and then these kappas help us understand how they're coupled. Okay, so if we were to think about how the mechanical mode is coupled, we would use this gamma M. So we don't think of a sort of transmission line port associated with the mechanics. We think of all of that information that leaks out goes to the environment, unless it's coupled to the electrical or optical mode. And then we would describe the coupling to the environment for the optical mode as this kappa O internal, right, the internal part of that kappa. And then we have kappa E internal over here. Then we have a coupling between the mechanical and optical system. and a coupling between the mechanical and electrical system. Those are the bare G's, but then I can enhance those by the pump. And then if I think about what is the coupling to the propagating modes, okay, then I have my kappa E external and my kappa O external. All right, so this is sort of engineering, but it's engineering that gets complicated and where we have to worry about this environment and what those different rates are. And ultimately, what we care about finding is, in electrical engineering language, I would call this the scattering parameter, or scattering parameters. There's 4 of them for a 2-port network. And what we might be particularly interested is this S parameter that would correspond to C out of, say, omega over A in. Right, so that would tell us about if we stuck some signal in a microwave domain, ultimately from the qubit, what would we get out in the electrical domain? And this is very much in the limit of, I'm thinking about a coherent state and what are those relative amplitudes. So that's what we might want to calculate. And oh, there's my environment. Okay. So if you go through and think about these different rates, there's this same rate that keeps popping up over and over again, this sort of photon-phonon exchange rate, cooling rate, coupling to the optical system. And for the electrical, it would be 4 alpha squared GE over kappa E. And I think about this as sort of the coupling to the propagating mode. And for the optical system, remember we called that amplitude chi. And so then we have these 2 rates. And those 2 rates, if I were to draw sort of a spectrum of what's going to happen here, this hash refers to, okay, so this is a function of frequency, and this is a big gap in frequency. So down here, we have the microwave mode, so that's the variation in density of states there. And then up here we have the optical mode. And we're going to have our alpha pump here, and then we'll have our chi pump here. And then what we want to do is end up transducing some small fluctuation that occurs sort of as a sideband with respect to each of those guys. Okay? Classically, I can think of this as sort of I put another tone in there, and then there's the amplitude modulation in the cavity, and then that drives the mechanical element a little bit, and then I read that out over here as a sideband. Okay, that's the sort of hand wavy argument. Okay, so that's sort of how the system will work, and if we go through all of these equations that I talked about earlier, what we would find is these scattering parameters. So between, say, electrical and optical and electrical, they'll end up being related to these different rates, to these electrical and optical rates, and compared to the sum of all of these damping terms. And then there's an efficiency factor and a gain factor there as well. So we want it to be very efficient. So we want this eta to be 1. We also don't want it to have any gain, so we want that to be 1. And if we stare at this expression for a moment, if you remember back to the parameters for this mechanical system compared to these sorts of rates. So these sorts of rates, when we put a decent amount of photons in the cavity, will be scale of tens of kilohertz, and this gamma m, that sort of bare coupling of the mechanical system to the environment, is more like Hertz scale. So when I look at these rates all by themselves here, then I can actually just get rid of this gamma m there. And so now I can look at this expression and say, so I have a knob in my system, or sort of how I operate this converter, in the sense that I can define these 2 pumps, right? So I could put a different amount of light into either of them. And in fact, I can turn on and off the coupling by turning on and off the pump. right? Because these numbers will be quite different depending upon what that pump is. So I could choose to turn up the optical pump to some value, and I could turn up the electrical pump to some value, and what should I choose, right? And actually it turns out what I want to choose is these two rates to be the same, and I think of that as sort of an impedance matching condition. Okay, so when those two rates are the same, if I were to just look at this equation, well, for good measure, I can write it out. I have 4 gamma O, gamma E over, or if I call those both gamma O, then that's squared, and then that will actually be 1. Okay, and the limit that I have perfect efficiency. So this impedance matching condition is what I want to get unity conversion between the two domains. So it'll also turn out, if I think about what is the total damping rate or this coupling for this coupled electrical and optical system, then I will ultimately care about a number which is gamma O plus gamma E that I'll call gamma total. And that'll end up being the bandwidth of the converter. And for these experiments, for the amount of photons that we typically put in, this is on order of sort of at max 10 kilohertz, and sometimes less than 1 kilohertz when we're trying to eke out information from these systems. So it's a very low bandwidth system, but maybe not crazy bandwidth compared to what you might run into for certain superconducting qubit systems. Okay. All right, so let's see. So in these measurements, this is getting into sort of experimental perspective, and I said there would be a lot of electrical engineering here, and so let's talk about that even more. So we have this converter down there, and we have all of this optical stuff that leads up to it, and we have all of these microwave lines here, and then this box here. And if we want to extract what is the efficiency, sort of port to port, meaning this microwave cable here, and wherever that optical hole is there, but that doesn't include the loss in the cables over here, or some efficiency of this path right there for the moment, just to characterize the efficiency of just the converter box. Then it turns out that it's helpful to think about different tricks that you could use in order to calibrate your system. Okay, so I mentioned this because this is what we spend a lot of our time doing. So I think I mentioned yesterday, or maybe I didn't, in the context of these systems where all we do is create Gaussian states, right? We spend a lot of time calibrating noise because if I have laser noise and it sort of looks white and it's sitting on top of shot noise, then I can't really tell the difference between those two. So we spend a lot of time calibrating that h bar omega over 2 is really what we think of it is. And then similarly with the efficiency, there's no sort of absolute scale that we can use to understand this, other than squeezing is a good way. But for this, we use a network analysis and really try to calibrate the system. So if you imagine that we have our network here, but then we also have all these other cables and stuff that also might have some loss that I'm describing here as, say, alpha and beta and delta and gamma, then what are some tricky ways that I could use in order to calibrate out those and really make sure that I understand what's going on? And the ideas that we use stem from things like long discussions with Michel Devereux. So he has a lot of good ideas as to how to do these type of things. One thing that I can imagine doing here is if I imagine that I measure in one direction, then I might get this factor of alpha, and then this SOE, and then a factor of delta if I want to measure what C out is. And getting that alpha and delta product is actually sort of hard, but if I imagine that I take the product of doing that with the sort of opposite possibility, which is my gamma times my SEO times, say, this beta, that's the loss over there. And then I'm able to, by measuring off resonance, I could measure what the product of alpha beta is. And same on the other side, I could measure delta gamma. Then I could divide this whole thing by those factors here. And then I see that in this whole blobbed up expression, then I see all of these different cable losses actually cancel out. So this is a way to extract this times this. And these will turn out to be the same in our experiment. And so that gives you an absolute scale for what's going on and allows us to calibrate and accurately know what the efficiency is. Yeah?
So just going back a little bit, when you said bandwidth of the converter, this applies to both the microwave frequency signal that you're sending in and the optical, or am I thinking correctly?
Yeah, so I mean it refers to if I tried to put in a tone at a certain frequency in the microwave domain and convert it to the optical domain, how far could I shift over and have the converter still work okay?
And the same
So
applies if I send in an optical and
yeah, so everything is symmetric in that way. Gamma E and gamma O come in the same way, and we really do want to show and hope this is bidirectional. Everything should happen the same way in both directions. And in fact, in a moment I'll show you. Oh yeah, there's data that shows that actually these S parameters that we measure are actually exactly the same in both directions. Okay, so these are these scattering parameters that ultimately come from looking at ratios of, say, C out to A in or A out to A in and squaring those. And what we see is SOE and SEO are those purple curves there. And we can see that they're basically the same. And the peak efficiency is at the mechanical resonant response. And if we go a little bit off, then it's not as good. And what we can also see, I focus on the blue one there for the moment, is that when we originally stick a signal in but don't have this impedance matching condition that's going to sort of suck energy out the other port, we can see a lot of light is reflected from the electrical port, and that's what the gray curve is. But then we can see that reflection go down or dip when we actually get the optical signal out the other side. The optical domain is a little bit more complex due to some various detuning factors, but the same sort of idea there. And we can actually see the efficiency change with this impedance matching condition. So we have, we're just varying one of the electrical or optical coupling rates, and then we're looking at the efficiency, and we see that we can get the best efficiency in a certain portion of setting this impedance matching. And so currently we're able to get the efficiency of the actual converter box up to sort of almost 50%. So that's sort of the scale of the efficiency that we're at right now. And what that's mainly limited by is actually kappa O internal. So the optics is the culprit when it comes to the efficiency. The optical cavity isn't quite aligned correctly, and so this kappa O internal compared to compared to, say, kappa O external, both of those are sort of 1 megahertz in the current experiments, because we don't perfectly control the light in the cavity, and that's what's giving us approximately this finite efficiency. Okay. All right, so now there's the topic of added noise. So even if I had a perfectly efficient converter, but I had some noisy process somewhere along the way, then I would measure that, let's say I put in a single microwave photon, I'd get a single optical photon out, but it would be on top of a bunch of other signal. And so we definitely don't want that. For the current devices, we're actually pretty excited that we're getting closer to a domain where we think that added noise can be small. So we're at a level of approximately 10 photons of added noise. And that's in comparison to the thousands we had a bit ago, and this is for a bandwidth of near kilohertz. But 10 is clearly not good enough, and so what is limiting this system? So there's multiple things that you can imagine can cause a problem. So we worked one of these into the equations that we've been talking about. So this thermal motion of the membrane that we're coupled through this sort of gamma m factor to the environment. And so if we're not decoupled enough from the environment, then this thermal motion will be a problem. And you saw yesterday that indeed it is possible to be in a domain where that thermal motion isn't important. That was basically the statement that we could cool the mechanics to the ground state. We could make that rate. Remember we talked about, okay, this keeps coming up again and again, this rate here, compared to what we were thinking of as a thermalization rate, right? So we found that we could make the ratio of those something that would cool to the ground state. But in our electro-optic converter, where we have to put tons of other elements in there and optimize many things, sometimes that doesn't turn out to be true. And so thermal motion of the membrane can be important. And we'll talk a bit about other ways of getting around that. But in general, we can also just make the mechanics better. Another thing that we've run into is, as within sort of all superconducting qubit devices, you're sitting on a solid state substrate, and you have solid state materials, superconducting thin films that are involved in the circuit. And if you don't do that just right, you'll end up with parameter noise in your LC circuit. And it actually turns out that we got a little surprised by the fact that when we put this whole thing together, and its geometry is a little bit different, and we needed different pumpings than you might typically need in these thin film LCs, that the circuit noise actually was apparently a pretty large component of this 10 photons. And so that's something that we're trying to fix. One of the things that we're suspecting at the moment is that it's actually, when we put the niobium thin film down, there's some sort of oxides on the surface that could be noisy, and we might try to switch to niobium tinitride. That would be a better material. Okay, and then the third one is what I think of as the thing we've ultimately been most scared about, and is perhaps sort of the most fundamental limit in some ways. Not quite fundamental, but very important in the sense that we have to have light down by where the superconductor is. And if any of that light hits the superconductor, that can be a problem. And it's hard to quantify, too, because quantifying very small amounts of scattering and understanding where that light goes is actually a very difficult problem. Like in LIGO, like we were talking about yesterday, dealing with very small amounts of scattering and where that light goes is one of the things that they definitely worry about, and is a really hard problem. What we try to do in our system, right, to mitigate this is that we're physically separating where the optical spot is and where the superconductor is. So that can be very helpful, but we still see sort of on the order of added noise of a few photons from the amount of laser light we need. So this is a plot of, if we turn the laser on and off and look at the noise quanta in the LC circuit, this is for one example experiment where we're increasing some beam power, and we have to sit somewhere along here to get the couplings that we want. Then we start to add quanta on the order of a few. And you can see this sort of structure where as we increase the power, it increases in this certain way. And this is something that we understand empirically, but sort of not fully theoretically. You can also look at how much the line width of the LC circuit changes when we turn on the laser. And so it adds about 30 kilohertz of loss in the sort of kappa. This corresponds to kappa, maybe using our same notation. This is kappa E internal change from the light that's hitting the superconductor. So this is good from a perspective of, okay, we don't turn on the light and everything dies, but there's definitely some effects that we have to understand in terms of where is this light coming from, how much light is actually hitting the superconductor, what different kinds of superconducting thin films could we use, how could we mitigate this scattering. Okay. All right. Any questions at this point? Because I think I'll move on to talking about sort of some more experimental data and different, more complex protocols that we're using. Yeah.
Can you talk briefly about how you measure the noise?
Yeah. So in this particular case, for example, you can see that we're looking on top of some amplifier noise that we calibrate ultimately by calibrating temperatures in the microwave system. In the optical system, we basically calibrate to shot noise, right? So we know very well where shot noise is, and then we find things on top of that, and it's not a trivial process. Yeah. Okay. All right. So let's talk about something that's maybe a little bit more interesting that we can look at in this system. So far I've talked about, okay, taking coherent states, sending them from one place to another, looking at noise in the context of just looking at the spectra and looking at areas under peaks, right? And so that's a lot of calibration and a lot of work to do that people in the lab spend a lot of time doing. But there's a little something more interesting going on here, and it's sort of related to some of the ideas we were talking about last time, where we said we have this optical mode coupled to the mechanical mode, and remember we created this ponder mode of squeezing, and that squeezing came from correlations between the mechanical motion and the optical shot noise. And what we can see in this case is in these data here, we have a mechanical system, but it's thermally occupied. Okay, so we're in a limit where we didn't perfectly get our mechanics right, so there's some thermal noise in the system. And if we just look at the optical fluctuations and the electrical fluctuations, they look the same, and we have some added noise from them. But there's something more interesting that you can see, which is that if you look at a cross correlation between your electrical port and your optical port, you'll actually see that in this thermally dominated regime, those signals are actually perfectly correlated, or near quite correlated. And so there's sort of a redundant record of the thermal noise in both the electrical and the optical ports. So that potentially provides some information. So let's say that I was trying to take some signal, the little blue squiggle there, convert it to the optical domain, the red there, and I was thermally limited, okay, in my converter from the coupling to the mechanics. Then I would get some noise on the output optical signal. But if I were to look in the electrical port, I have a record of that thermal noise in the electrical signal. So classically, I could imagine that I just subtract that out because I have information about that thermal motion. Now, in the quantum world, if I think about this optical port over here, I'm going to have vacuum on top of that electrical signal that I measure, and also I'm not going to be able to measure very well that electrical signal, or depending on the efficiency of my system, that might be an inefficient measurement. And so it won't necessarily be perfect from that sense, and if this ancilla is just vacuum, that's a problem for if I really wanted to use this for quantum states. Though what I could imagine is actually squeezing, putting the squeezed vacuum in that ancilla port, and that could actually help me, for example, upconvert one quadrature noiselessly, and that maybe could be useful. So, and Graham and others have been thinking about this. So what I can do is in this sort of classical limit, I can show that if I don't have this feed forward, I have a certain noise in my signal, but then I can subtract off some of the noise if I do use this feed forward process where I actually measure that thermal noise in the electrical port. So I can see this here in the context of I have different curves here. These different colors correspond to feeding forward that electrical signal to subtract out some of the noise in the optical port, with different weighting factors corresponding to how much of that signal do I subtract. And I can see that the black peak goes down to the blue peak. So I'm actually decreasing the noise here by 60%, while sort of keeping the cooperativity of the system constant. Okay, cooperativity, I guess I haven't really used that term, but that's basically this gamma opt compared to gamma thermal. And so usually I think about everything that I've told you over the last 2 days here. I want to think about that I need a certain sort of set of rates of those compared to the other one in order for this conversion process to work, in order for me to deal with this environmental noise. But efficient measurement is another way that I can do this in principle. And another thing that you can notice here though is, so you see how the blue curve, the background signal there, that imprecision, that's going up. And that's because I'm not very efficiently measuring the microwaves in this case, so it's coming from the microwave imprecision. So that does put a limit on how well I can do. And generally, measuring these signals at the sort of 99% level is going to be difficult, but we are getting better in terms of efficiency, so it's useful to contemplate this. And you can compare this to what happens if I just increase the laser power by doing laser cooling. In this particular case, there are technical problems related to if I increase the laser power, then I had more noise, and so I was actually able to do somewhat better or as well using this feed-forward technique. So that's an example of how measurement can be important and efficiency, and you can use that information. Okay, so that's some of the latest. Like I said, I'm not going to get to a point to telling you anything about quantum states that we transduce, but sort of what are the next steps? So we want to get rid of this added noise, make it more efficient, do a lot of engineering, understand how we couple to these various to the environment, and get rid of those couplings. And then experiments that we want to do are first sort of a continuous variables entanglement between the electrical and optical signals. But ultimately, if you really want to do something interesting, we're pumping this system, and you imagine I put a single photon in on this sideband, and I want to get a single photon out on the other sideband, but it's very close to a large coherent tone. And so what I would need to do is I would actually need to filter out that large coherent tone, or coherently cancel it, filter it, get rid of it compared to that single photon. And that's a non-trivial thing to imagine, but we think it is actually possible based upon sort of cavity technologies that are similar to the cavities we use here. So those are the kind of things that we want to do, and we'll see if it's possible to get to that domain. So these are the people involved in this electro-optics experiments, and this is sort of the experimental team, and Graham and Liang have been thinking about things with us as well. Yeah.
Where can you use the entanglement between microwave?
Yeah, so if I were to just do continuous variables entanglement between the electrical and the optical domain, what would I do with that? I would say that in itself is more of a statement of just demonstrating that it's all a quantum link. I think that if you actually want to do something useful, you would want to think about some sort of single photon thing, somewhere where you could herald the entanglement between distant superconducting qubits. And then you could ask, okay, let's say this all worked. What kind of state would I make? What would it do for me? Could I make something that's more robust against loss? What is a quantum network good for anyways? Those are all good questions. Yeah. Oh, sorry. Oh, yeah.
Yeah, so just a quick question about this feed-forward protocol. So here you're only doing it classically. So presumably you wouldn't be if you had this actual quantum conversion, then you wouldn't be able to remove added noise that way.
Yeah. So the one thing that we can think of, and Graham and others have been thinking about how you would really do this, is what you could do is, let's say you put in a squeezed ancilla, then you could upconvert one quadrature noiselessly, and then you would add noise in the other quadrature. But maybe you could do some sort of error correction to deal with the noise in the other quadrature, in which case it could be useful. But that's one thing that we're trying to figure out.
But you would still have the added thermal noise on your...
No, but that's what we're getting rid of with the feed forward. So you can really show that if you have a very efficient measurement, then you can really get rid of the thermal noise very well. Yeah, which was surprising to us in the sense that every single thing that we usually do, there's just sort of this basic law that you can't be coupled to that thermal bath or else you have a problem. But if you can efficiently measure, then it actually is quite interesting that you could get rid of it. Yeah.
Yes, compared to approaches, the depth scheme depends on your measurement efficiency, right?
Mhm.
And the other scheme depends on limited by the cooperativity.
Yeah.
So compared to which one you think will be more promising?
The cooperativity. I think practically we'll probably just fix the cooperativity. But I don't know. We'll see. Okay. Well, I think in the last minutes here, I was just going to preview a little bit of what I was going to talk about tomorrow, if there are any questions about optomechanics or measurement or transduction. Yeah.
Can you also comment on this the parametric process? When you have a finite, what's that? The kappa and the omega mechanical is comparable.
Oh yeah, right. Okay, so yeah, so the parametric. So we're using sort of a double parametric scheme in order to do this transduction, and like we talked about yesterday, in order to separate out this beam splitter from a two-mode squeezing, which is sort of like amplifying, then we need to be resolved sideband, and to really separate those two things out. And in all the experiments that we've done so far, we're really sort of on the border of fully resolved sideband. And so, like the data that I showed yesterday, the resolved sideband limit led to cooling to 0.2 phonons. So I think that in general, what we're going to try to do is push up the mechanical frequency and keep the cavities sort of similar. So we would really like to be at like 5 megahertz mechanical frequency and 1 megahertz for the cavity line width. And then you look at that ratio squared and it looks pretty good. So I think that's sort of how we'll solve that problem. Is that sort of what you're asking? Yeah. Yeah. Okay. All right. So yeah, just as a preview of some of the things that I can talk about tomorrow. So we're here next to Jilla, where many things that happen are related to ultracold atoms, and there's a lot of analogies between some of the cooling processes that we've been talking about and the cooling of atoms. And this is a picture of a Bose-Einstein condensate that was created, I guess it's over 20 years ago now. And those are sort of large-scale bulk sets of atoms that you can measure macroscopic properties of. And there's many different experiments that people have done in that domain. But they're, in the context of this sort of quantum information summer school, there's been a push in neutral atom systems to try to get to the domain where you're really controlling single atoms, and or measuring them or grabbing onto them. And this can be in the context of quantum gas microscopes, are often the way that people are doing this. This is a picture where if you were to look at the granularity of this picture, you would actually see sort of single atoms where you have a lot of them that are scattered about a lattice. So you're actually imaging single atoms in the lattice. You can control those atoms and do interesting sort of quantum information-y type things with them, but on the scale of, in this particular picture, 8 atoms or so. In our lab, we actually do some experiments where we use atoms and optical tweezers, and we, instead of making a Bose-Einstein condensate, throwing it into a lattice and looking at the atoms, we actually assemble these atoms together and then control their internal and external states, and then can use this in order to see what we can do with single neutral atoms. And so that sort of will be the topic of tomorrow. We'll talk a bit about how you entangle atoms maybe via Rydberg interactions is the strongest thing you can get with neutral atoms. But then also things that you can do where sort of these atoms are acting as an analog to a photon. So I think I sort of think of this as a single atom source instead of a single photon source. And what kind of things can we see? Yeah, and so we can, in our experiments, this is an array of many different atom traps, and in each of these traps we can grab onto a single atom, though this is an averaged image, and we can move them around too in real time. So this is making a a ring of atoms by capturing some atoms in each of the bright spots of a single atom, and then you can sort of move them to where you want. And so this is sort of a domain of control of neutral atoms, where we can talk about prospects for how many atoms you could do this with and what kind of couplings you could get between them, and how I could think about them as a qubit and how far they are from a good qubit, and doing the good 2-qubit gates. So yeah, I think maybe I'll end there as a little preview of next time, and we'll go into anything beyond that. But yeah, I'm happy to answer other questions or. Okay, I'll see you tomorrow.